name is electrostatics. Sorry. Our topic name is electrostatics of conductors. And every word you write, every term you write, try to understand the meaning. Electrostatics means when charges are at rest, then how does conductors behave? So we'll do it in a mind map fashion. Conductors. Conductors are supposed to have mobile charge carriers, and that is the reason they conduct. Okay, they will have mobile charge carriers, and these mobile charge carriers, and write the notes exactly in this fashion only, are nothing but free electrons. Okay, and these free electrons move freely inside the conductor. Make sure you're understanding what you're writing. Conductors have mobile charge carriers. These mobile charge carriers are free electrons. Okay, so when we talk about conductors in this chapter, we are going to talk about metal atoms. Metal atoms. Metal atoms have, now our discussion will be on the charge carriers, which are the free electrons. So let us talk about metal atoms and how their electrons are. There are two types of electrons. One is known as inner electrons, and these electrons are bound to nucleus, right? And then on the other hand, we have valence electrons, and these valence electrons are loosely bound. So when you learn later, your study becomes easy. And since they are loosely bound, we say that they detach from individual atoms. They detach from individual atoms. This means this is the process when they become delocalized and become common to entire metal. Children, what do we mean in this step? In this step, we are trying to mean that the atom electrons have become now delocalized. Clear? Okay. So if I look at metal atoms have got fixed positive ions. Achha, how do you say fixed positive ions? There were atoms whose valence electrons have now detached. If the valence electrons have detached, then the metal has fixed positive ions. Okay, these are atoms that lost electrons. These are atoms that lost electrons, and along with them they have large number of free electrons. Large number of free electrons, and these free electrons move randomly. They move randomly throughout the metal. And behave. Please understand, they behave. They are not. Behave like a molecule of gas. Molecule of gas. And this gas is known as electron gas. Don't think that electrons have turned into a gas. Have you understood? It's like a cloud of electrons. So it is analogous to as if a molecule of gas, and this gas is known as electron gas. Is this clear? So we have got metals. Metals are conductors. Metals are classified by their mobile charge carriers, which are free electrons. These free electrons move freely in the conductor. Such electrons of a metal atom can be inner electrons which are bound to the nucleus. That's not of importance to us. The ones those are loosely bound are the valence electrons, and they remain loosely bound so that they can detach very easily. When they detach, they move through the entire metal atom as a gas, and that gas is analogous to an electron gas. So metals have got fixed positive ions and a large number of free ions. Is this clear? Okay. Is it helpful? Because if we write it elaborately, I think it becomes much more helpful than your when you study them for short answers. It becomes easy. So now we see the same. You see the same metal atom. Okay, metal atom means basically you are seeing the free electrons, and you see the free electrons under two circumstances. Okay, the first one is when no electric field is applied. Suppose there is no electric field at all. In such a case, electrons move in all random directions, such that the average motion is zero. So no current flows. Okay. And the second one we see when an electric field is applied, and say towards the right side. Say you have applied an electric field to the right side. Okay. Then what will happen? Free electrons experience a force, like grandma's story, and this force is given by Q times of this, opposite to the electric field. Achha, did you understand why opposite to the electric field? Because it's an electron. Electric field's direction, always a positive charge will go. You're talking about free electrons, which are negatively charged particles. They experience a force which is opposite. Something interesting happens. Electrons still continue to move randomly, but they acquire, this will be important in your next chapter, they acquire a small average drift velocity. Drift velocity means when you throw a lot of, say, leaves and into a river which has got current, the leaves are seen to be drifting away. So the electrons, though they move randomly, but they are slowly acquiring a drift velocity which is opposite to the field. Opposite to the field. Due to this reason, they will produce an electric current. So let's understand this. Once you apply an external electric field and say the electric field is to the right, then every electron will experience a force which is opposite to the direction of the electric field. That is, they will feel the force towards the left side. The electrons still continue to move randomly as they were moving, but slowly all the electrons will be seen drifting. They will drift with a small average velocity opposite to the field and will produce an electric current. So you can write it that while the electric field was in this direction, the drift is in this direction. Positive ions. Children, you have not written anything great. This is actually the grade 10 thing that you are learning. In grade 10, we used to say when you apply an electric field or you apply an electric current, then what happens? Whenever you apply an electric field or you apply an electric current, the conductors will start feeling the electrons will feel a force which is opposite to the direction of the applied field, and they will start drifting and a small current will be produced. If you remember, in grade 10 we used to study electron current and electric current. Electron current is always opposite. So the positive ions are locked in the metal lattice or the crystal lattice, and current flow in metals is due to free electrons. This actually tells you who is responsible for the flow of current in metals. Only free electrons. Whereas somebody might ask you a 1-mark question that what is it different from an electrolyte? In an electrolyte, both type of charges are actually flowing, cations as well as anions. But in a metal, there is only one type of flow, and that flow, one type of particle which flows, and those particles are known as free electrons. What happens now? Just try and understand. I'm a metal atom. My free electrons or my valence electrons left me. Your valence electrons left you. His valence electrons left him. All these valence electrons have now formed the electron gas, and they keep on moving randomly when there is no external field. When an external field is applied, then what happens? These electrons start facing a force which is opposite to the direction of the field. And though they still keep moving randomly, but all of them will start to drift in one direction. That drift produces a current. Now you can ask, sir, what happened to the positive ions? That means me after losing my electron, but I cannot leave my position because I am a part of the crystal lattice. So I remain locked, whereas my free electrons are actually contributing to the current flow in a conductor. Hence, in a conductor which is a metal, the current flow is only due to metal. Is this much clear? Now, after that, write down a statement. I will narrate it. Conductor or conductor, just write the singular. Conductor contains free electrons. Conductor contains free electrons that move freely inside the conductor. That move freely inside the conductor. Once you have written that line, just stop and take a moment to read what you wrote. A conductor contains free electrons that moves freely in the conductor, right? No issues. Now understand, what were the two things we studied? What you wrote is now only the left part of the diagram. The right part of the diagram was when this conductor was exposed to an electric field. Then what did these electrons do? They all started to move. This is actually called, they all start to redistribute themselves. So our next line would be their redistribution. Their redistribution means the redistribution of the free electrons, right? Their redistribution under electric forces gives rise to all electrostatic properties of conductor. Gives rise to all electrostatic properties of conductors. Take a moment now. What are we going to study? We are going to study electrostatics in conductors, means you will study properties of conductors in electrostatics. How these properties are created? Children, these properties are created whenever a conductor which has a lot of free electrons is exposed to any electric force that can be created by an external field, then these free electrons show a lot of regrouping or redistribution. This redistribution will create many type of properties in them, and we are going to study those properties, 6 of them. Shall we start with the first one? Okay, the first property is electrostatic field inside a conductor is 0. Electrostatic field inside a conductor is 0. This actually gives birth to something which is known as electrostatic equilibrium. means charges are at rest. Understand, if I have a conductor, if this is a piece of conductor, the electrostatic field created due to charges E inside is equal to 0. We're going to write about this, okay? So let's first write the inference statement, and after that we will draw our criteria. Okay, write the inference statement. It says electric field inside a conductor is 0. What you are writing right now is an answer to a question. Why is electrostatic field inside a conductor 0? So you're writing an answer to that. Electrostatic field inside a conductor is 0. Inside a conductor is 0 because electrons rearrange themselves in such a way Did you remember you wrote one line, redistribution? All these will be rearranged themselves in such a way that electric field inside the conductor is cancelled. When you make our answer a little bit more heavy now, if the field were not 0, means if E inside were not 0, if the field were not 0, think now, inside this field is not 0, then charges inside will feel a force which will be opposite to the field, and if they feel a force they will keep moving, which is against electrostatics, because electrostatics says charges are at rest. So we wrote, if the field were not 0, charges would continue to move. And the conductor would not be in electrostatic equilibrium. Right? Let's see an explanation of this now. Since you have written your part, let's see the explanation part, okay? So again, very in simple language, I have a conductor and my conductor is classified with many free electrons, okay? Now suppose there is an electric field. So if you have an electric field, these many free electrons will start to experience force. You can write this, and this force will be given by QE. And due to this force, they will start to move. But this entire thing is a contradiction. This is a contradiction to electrostatics, which means charges are at rest. Electrostatics says that charges are at rest. So electrons rearrange themselves till the E internal exactly cancels the electric field, and cancels the electric field. This electric field is this one. Suppose there is an electric field. It exactly cancels this electric field. Hence, it is proved that E inside is equal to 0. Clear? We'll make one more assessment of this, because based on this, some Gauss law things will also come now. So, suppose your conductor is charged. So, you have a conductor, same explanation, and this conductor is, say, suppose, it is charged, may be charged. What happens in that case? Charged means it has got excess charge. Excess charge means these are also some free electrons only. Understand, there is nothing other than electrons. These electrons will be repelled by the electrons which are inside. Electron-electron repulsion happens. There is an electron-electron repulsion. As a result, the excess charge, this is another property we'll study a little bit later, excess charge will spread to the surface. See, children, you have to prove that inside the conductor electric field is 0. The first conductor that you took, the example that we wrote just now, was a neutral conductor. Now we have a conductor which has got excess charge in it. That means my conductor is already charged. Whenever you charge a conductor is supposed to have excess of charge. That's why it is charged. Say, suppose I was having 100 positives and 100 negatives. Then am I charged? No, I'm neutral. Now I'm having 5 extra negative charges. I'm extra charged. So where are those 5? Those 5 will be repelled and they will come onto the surface, which again tells you that the electric field inside is equal to 0. Means inside how many charges you have? Equal number of charges. So the electric field inside a conductor is 0. So write down this line. Inside conductor, very important. Inside conductor, E is equal to 0. Whether you are a neutral conductor, whether you are an external conductor. Now suppose you are the second one. Now suppose you are a conductor where you have actually applied external electric field. You have applied an external electric field. Now due to this external electric field, induced charges will be produced. The positives will be actually going in this side, leaving the negatives on this side. So you will have one more electric field internal which will be created. And how long this internal electric field will be created? As long as it doesn't match the external electric field. At one time, the internal and external will cancel each other and will again bring you to the scenario where E inside is equal to 0. So did you understand what you wrote? Inside an electric conductor, whether the conductor is charged, whether the conductor is neutral, or the conductor is exposed to an external electric field, the electric field is always 0. If you want to write for this, you can write down, if external electric field is applied, this is if external electric field is applied. Can't help it, children, this is theory part. If external electric field is applied, free electrons move. Just write down in steps. Write down in steps. Free electrons move. Then you write accumulate on opposite surfaces. Charges accumulate on opposite sides or surfaces. This is called induction. I hope you know what is induced charges. These charges were induced. Induced charges create an internal electric field. Third point, induced charges create an internal electric field. Induced charges create an internal electric field. Both electric fields cancel inside the conductor. Induced charges create an internal electric field. Both electric fields cancels inside the conductor. So our point number 1 is done. Take a moment to understand whether you have understood or not. It's not just about writing. The electric field inside a conductor is always 0, whether you are a neutral conductor, whether you are a charged conductor, or you are a near an electric field. Neutral conductor, how do you satisfy? In neutral conductor, you said, suppose there was an electric field. If there is an electric field, all the electrons will be facing a force which is opposite in direction, and that will create an opposite electric field. So both will cancel each other. If I was charged, then my excess charge is always on the surface and there is no extra charge inside. Electric field is equal to 0. If an external electric field was applied to me, in that case also, my electrons or my free charges will get induced in such a manner that there will be opposite charges created on either sides. An internal electric field will be set up. This internal electric field will actually cancel the external electric field inside the conductor. So bottom line is, for a conductor, the electric field inside is equal to 0. Is this point clear? 6 of such points, 1 point gone. Next are easy. Okay, now tell me, the next point is very easy. If you are charged, then what do you have? Excess of charge. Where is this excess of charge? It lies on the surface. The next point is with that only. So write down. At the surface of a charged conductor, at the surface of a charged conductor, the electric field is always perpendicular to the surface. When the surface is charged, the electric field is always perpendicular to the surface. Or you can show like this also. If you are a charged conductor, the electric field E is always perpendicular to the surface. Now, why does this happen? Okay, now let's understand. Let's write the answer to this. Have you understood? If you are a charged conductor, there is charge on your surface and the electric field is always perpendicular to the surface. Why is it so? So we write, at the surface of a charged conductor, at the surface of a charged conductor, the electrostatic field must be normal to the surface. At the surface of a charged conductor, the electrostatic field must be normal to the surface. At the surface of a charged conductor, the electrostatic field must be normal to the surface. So it's something like this, children. You are trying to say that at a surface you have an electrostatic field which is always normal to the surface. Now we'll go by method of contradiction. Say it is not normal. It is something like this. Then it should have two components. One component along the surface which is known as E tangential, and this is the E perpendicular. Have you understood? So we write now, if the field had a tangential component, means if you had ET, free charges on the conductor. So listen, children. Say suppose I have got a lot of free charges. Let these be positive charges only. Let these are positive charges on the surface. If you have a tangential component, then don't you think these charges will face something, a force called QE, and QE will actually take them on this side? But in electrostatics, charges cannot move. So this contradicts the thought process that there is a tangential. So if there is no tangential, the only possibility is that you should have only a perpendicular. So that's what we are writing. If the field had a tangential component, free charges on the conductor would experience force and move along the surface. Since charges are at rest in electrostatic equilibrium, the tangential component must be zero. Thus, electric field on the surface of a conductor is always perpendicular to the surface. So electric field on the surface of a conductor is always perpendicular to the surface. Want me to repeat once again? Are you fine? Okay. So look, if I do this as a vector diagram, I would write E is the vector sum of E perpendicular plus E tangential. And you just said that this is 0. Therefore, you have the only E that is present is the E that is perpendicular to the surface. Did you get? So write one line like this, like you wrote inside the conductor E equal to 0. You write another short with a red pen. E is perpendicular to the surface. So see, actually you learn two very small things, but we are going elaborate because a lot of questions come from here. If you are a conductor, the electric field inside you is 0. Whether you are a charged conductor, whether you are a neutral conductor, or you are a conductor whose vicinity you have electric field. That was point 1. Point 2 says, if you are a charged conductor, that means if you have charges on your surface, you can have only one type of electric field, and that field is perpendicular to the surface. You cannot have any other electric field. So there is no tangential component. Fine. Let's go to the third one. The third point. Interior of a conductor can have no excess charge in static condition. Interior of a conductor can have no static charge, can have no excess charge in static condition. See, when you keep on writing, sometimes the brain dies. Can you just read the last statement that you wrote, the third point? Third point, no, the third property of the conductor. Interior of a conductor, no excess charge. Your brain is not working. Now start thinking like this. What was the first point you wrote? First point, the very first point today. First point was E inside equal to 0. So look at me. I have a conductor, which is this water bottle. I say there is no electric field inside. What is the third point you have written? There is no net charge inside a conductor in static condition. Go by Gauss laws. What does Gauss law say? E dot ds is equal to Q net inside over epsilon naught. If your E is 0, ds cannot be 0. So on your right hand side also you have to make it 0. So how do you make the right hand side 0? Epsilon naught cannot be 0. So what is 0? Q inside is 0. Alright children, see, don't confuse so much. In the first law you said that the E inside is equal to 0. In the third property you are saying that inside of a conductor there is no net free charge is equal to 0. Both actually support each other. If you say Gauss law says that the flux, if there is charge, there will be flux. Flux is given by E dot ds, which is also equal to Q inside over epsilon naught. You are saying that this is 0. E inside is 0. So how do you, if this is 0, this becomes 0. How do you make this 0? This cannot be 0. So this has to be 0. Yes or no? Right? So we write our statement. Excess charges cannot exist inside a conductor. Excess charges cannot exist inside a conductor in electrostatic equilibrium. This is what you are trying to say. Mind you, all these things will get defeated if the equilibrium is defeated. Right now it is in electrostatic equilibrium. What does electrostatic equilibrium mean? Charges are at rest. If the charges are at rest, excess charges are not allowed inside. And if you have excess charges still, where should be they? On the surface. And in such a case, they will create an electric field which is perpendicular. So you write the next point also. If there are any excess charges, if at all there are any excess charges, they will always reside on the surface when a conductor is charged. अरे भाई एक्सेस हो ही नहीं सकता है. If I've got 100 plus, I will always have 100 minus. It says that inside 100 plus and 100 minus give you a net condition of 0. But you are saying, sir, if there are still some plus 5 charges, then I'll say that means you are charged. And if you are charged, where should your charges lie? On the surface, right? So you can write the proof for this, very one line proof. The property 1 tells you E inside is equal to 0, right? So the flux, the electric flux is given by E dot ds or dA, whatever it is. This is equal to 0. However, the electric flux is given by E dot dA as per Gauss law, which is also Q inside divided by epsilon naught. Therefore, Q inside must be equal to 0. Or Q enclosed, whatever is the word you use. Excess charges come to the surface only because of the fact that an electron repels another electron. So write down, electric field inside a conductor is 0. Electric field inside a conductor is 0. So electric field inside a conductor is 0. So flux through any closed surface, electric field inside a conductor is 0. So flux through any closed surface inside the conductor is 0. I'm just writing the language description of these things. Okay. So flux through any closed surface inside the conductor is 0. We can put an arrow which implies net charge enclosed inside is equal to 0. So time to write this also. The first thing, what did we write as slant? E inside 0. Then we wrote E is perpendicular to surface. Now you write, for this point you write excess charge always on surface. Excess charge always on surface. Excess charge always on surface. Let's go to the fourth point now. The fourth point is electrostatic potential. The fourth point will talk about electrostatic potential. Write down, the electrostatic potential is constant. Electrostatic potential is constant throughout the volume of the conductor. Throughout the volume of the conductor, and has the same value as inside and has the same value that as inside you put in bracket and has the same value as inside in bracket on its surface. So what you are trying to say here? You're trying to say that if you have a conductor which is in electrostatic condition, the electrostatic potential is same inside as well as outside. There will be a potential, but the electric potential is same. If the electric potential is same at every place inside, what about the potential difference between 2 points? 0. What about the potential between 2 points inside? 0. What is the potential difference between 2 points outside? 0. So you can write, this whole statement can be made into a short line. A conductor is an equipotential body. You remember equipotential surfaces? So a conductor is an equipotential body. Body means whether you touch the surface, potential is same. Whether you touch inside, potential is same. A conductor is an equipotential surface. Now let's see how this happens diagrammatically. Okay, so we have a conductor. So there are two possibilities. If we look at inside, children, what did we say? That inside and outside the potential is always zero. It is equipotential. Let's look at inside. At inside, the electric field inside is equal to zero. If the electric field inside is zero, then the work done, electric field inside is zero. Therefore, the force that you will experience is always equal to the Q inside, and this should also be zero. What do you understand by potential? Potential is the work done. The work done in moving a charge from one point to the other. So work done is given by what? Say you are moving small distances dx and you multiply it with f dot dx. If your f is 0, so your work done is also equal to 0. You are doing no additional work at all. So if you don't do any additional work, that means the VB minus VA should also be 0. This is the explanation. Right? Because VB minus VA is nothing but W divided by the charge that you are trying to move, and W is 0. That means this is equipotential. That means PD must be equal to 0. This is inside. And you said on the surface also it is the same thing. So you look at the surface. On the surface, what happens on the surface? You just said any tangential electric field is 0. So same story. Any tangential force is also 0. And work done to move on the surface should be equal to the integral of tangential force into some displacement. When this is 0, work done is 0, which means VB minus VA, which is equal to work by a charge, is also equal to 0. Therefore, PD is equal to 0. This is the explanation. See, in textbook, if you read now, these explanations are not there. This is to make, you will just read it as paragraphs. Go and read the paragraph in the textbook, it will confuse you like anything. Now your job is become easy. Inside, no work done. Outside also, you don't do any work. Acha. There is a third thing. You can say, sir, on the surface, I do have a E which is perpendicular. I do have a E which is perpendicular. Very good. In that case, the force experienced by you is QE perpendicular. So the force is also perpendicular. The force is also perpendicular. Do you agree? So the work done will be given by what? Integral of the perpendicular force into dx. And what is the dot product? F dx cos theta. Theta is 90 now. So your work done becomes F perpendicular dx cos of 90. And still your work done is 0. Now we are neck and crop proofed. If you have an electric field, if you look at the surface always has a perpendicular field. If the field is perpendicular, the force is perpendicular. Means what you are trying to do here is that this is your surface, the field is perpendicular. You are trying to take a charge and you're trying to move it from this point to this point. What is the direction of the force? Perpendicular to the displacement. Work done is 0. Is the explanation understood? Right. Come, number 5. Done with this? Once you read it in Thanda Dimag, you will understand everything. Number 5. Electric field at the surface of a charged conductor. Electric field at the surface of a charged conductor. When you're trying to say surface means a little bit outside the conductor, okay? Electric field at the surface of a charged conductor. The electric field is given by sigma by epsilon naught, and we put a normal. You just said, na, the electric field on the surface of a charged conductor is normal to the surface. So what is the value of that electric field? The value of that electric field is sigma upon epsilon naught, and you are putting the normal n unit vector, means it is normal to the surface. Children, what we are trying to say is simple like this. This is a conductor surface which is charged. You said that with the surface, the E tangential is 0. There is always a perpendicular component. This perpendicular component is given by sigma by epsilon naught. And this is what you are trying to say. Sigma is surface charge density. Sigma is surface charge density. Write down sigma is surface charge density. So here we will, this is a classical case of one Gauss law application. So this is our charge conductor. Right? We have to assume a Gaussian surface. The Gaussian surface is like a small capsule pill. It can be cuboidal, it can be circular. Try and imagine, okay? So this is one side and this is the other side. It is, the Gaussian surface is actually a cylindrical thing which is in and out. Are you able to understand? This is in and out. And only this portion is the charged portion. This portion is the charged portion. Agreed? Right. So how is the electric field going to be here? The electric field will be normally coming out of this surface, right? This is the electric field, and we have to prove that this electric field is this. Very nice. Let this charge area be something like ds. Let it be ds. So the surfaces will never contribute to any flux because the surfaces are perpendicular to this electric field. Only this one is going to contribute to the flux. So what is the flux of this? Tell me. As per Gauss law, the flux contributed will be given by E into ds. Right? And EDS should be equal to what? The Q enclosed divided by epsilon naught. Right? Acha. How to get the Q? So from here we get E into ds should be equal to Q enclosed upon epsilon naught. Now look, children, what is the surface charge density? The surface charge density is always given by the charge spread over the entire area. Right? We want to find out what is Q enclosed. Our area now is a small area ds. So this is our Q enclosed. This will also give the density, right? Density is density. Density has nothing to do with area. Density is charge per unit area. How much charge is here? Q enclosed. How much charge is here? Q enclosed. What is the area of it? ds. So can you find the value of Q enclosed? Q enclosed is given by sigma ds. So can I write this as sigma ds divided by epsilon naught? Ds cancels, you got your idea. E is equal to sigma by epsilon naught. And if you write it in vector form, it is sigma by epsilon naught, normal vector. Did you understand the explanation or not? So here we say that this is your surface. The Gaussian surface is a pillbox. You can write it as a pillbox, or you can say, let us consider a small portion ds, and the Gaussian surface is a pillbox which is protruding through it. Children, Gaussian surface is like this. See, this bottle inserted inside it. So this much portion of the charge is contributing, which is sigma into ds. Achha, one more question. If this would have been negatively charged plate, the electric field would have been inside. Positively charged, the electric field is outside. 5 minutes and just one last point. Another such theory thing is potential and dielectrics and polarization. After that, we get back to our capacitors. Last point, okay? So what all points did you study so far? Point number 1, E inside 0. Point number 2, on the surface, if it is charged, E is perpendicular to the surface. Point number 3, what did you study? That there cannot be any excess charge. Point 1 contributes to point 3. Point 2 will contribute to point 4. Point 4 says that the voltage is always same, equipotential. It is equipotential. That is coming from point 2 because you don't have any surface electric field, no tangential. Okay. Now then point 5, any point 5 we said that if you have a tangential compound, what we call perpendicular electric field, its value is given by sigma by epsilon naught into the n unit vector. The last is electrostatic shielding. Electrostatic shielding. So we'll just write about it. See, electrostatic shielding is something like this. If you have a metal shell, the inside of it is shielded. Inside is shielded from anything that may happen outside. That means that globe, the globe that you see, this is, and you suppose there are some electronic components kept inside the globe. This is to be known as Faraday's cage. Keep anything inside that and put huge amount of electric field on it. Nothing will happen. You don't believe me? Have you ever flown in a flight where there has been thunderstorm? The flight is a metallic body. Why did you not get the shock? Because you are electrostatic shielded. You are inside a Faraday's cage. So when the aircraft comes and lands, the first thing they will do is put a ground cable with the aircraft because you are not supposed to touch the aircraft. An aircraft may carry huge amount of static charge. So when the aircraft refueling will happen, they will never connect the refueling because there might be a spark and everything might go off. The first thing they will do is connect a ground cable, decharge the entire aircraft, all the charges, then the refueling starts. You are driving a car and it is raining torrentially. Thunder strikes, you don't die. Why? Electrostatic shielding. So we write it. Electrostatic shielding is a phenomenon. Electrostatic shielding is a phenomenon in which electric field inside a conductor's cavity electrical field inside a conductor's cavity. Have you understand the cavity? The cavity is the fuselage of the aircraft where you are sitting. Inside a conductor's cavity remains zero irrespective of external fields or charges on the conductor. Put a lot of charges on the conductor, connect it with some electrical wires, nothing happens to the inside. Okay. Electrostatic shielding is the phenomenon in which electrical field inside a conductor's cavity remains zero irrespective of external fields or charges on the conductor. Irrespective of electric fields or charges on the conductor. Have you written that? Further, the free charges on the conductor. See, a conductor will always have free charges. The aircraft body has got free charges. Think it like that. The free charges on the conductor redistribute themselves on the outer surface. So what has happened? You have got an aircraft body and you have put electric field. Excess charges come or you have put. So the free charges redistribute the free charges on the conductor redistribute themselves on the outer surface and cancel the effect of electric fields inside the cavity. And cancels the effect of electric field inside the cavity. Hence, cavity remains shielded from external electrical influence. Hence, cavity remains shielded from external electrical influence. This principle is used in protecting sensitive electronic equipments sensitive electric equipments. One explanation, 5 minutes are there and then we are done. Okay, let's see the explanation. So sensitive electric components or components. You have designed a cage now in which you are keeping your pigeon or the parrot. Okay, So let's see a conductor. Now you have a conductor, and the conductor has a cavity, something like a globe. The conductor has a cavity, and a cavity is something which is known as a hollow space. Right? You have a hollow space. And the hollow space has got no charge. No charge. So obviously the E is equal to 0 by Gauss law, because E dot ds is equal to Q inside by epsilon naught. Q inside is 0, so E naught is 0. So it means no matter, and here the cavity is no matter how large, what shape, and blah blah. No matter how large, what shape, how much charge is on the conductor. So this is my conductor, and this is the cavity. So whether you have any shape, any charge, how much is on the conductor. So we say a conductor with a cavity can have two scenarios. If you have an external electric field, suppose there is an external electric field, so free electrons, you just wrote this, free electrons redistribute such that E external equals to E internal. Therefore, E becomes equals to 0. So E cavity is also equal to 0. And suppose it is a conductor which is charged. You have charged. So excess charge, this is on surface. This is point number 3. If a conductor is charged, excess charge is always on the surface, no charge inside. So E inside is also equal to 0. Same conclusion. So here what do we write as our slanted thing? Write that beautiful line. Conductor is an electrical umbrella. A conductor is an electrical umbrella. So as we wind up, just one time, once you have written, let's have a quick, very quick, less than 30 seconds revision. Conductor is an electrical umbrella. So what did you write? Just see. If you are a conductor, electric field inside is 0. Whether you are charged, whether you are neutral, whether you have an electrical field in your vicinity. If there is any excess charge, then the electric field is always on the surface, which is perpendicular. Then third, what did you see? No excess charge inside the conductor. Any excess charge always on the surface. Fourth, what did you see? The entire conductor is a equipotential body, because on the surface there is no field, no work done. Inside, no electric field, no work done. Potential is same, so potential difference is 0. Then what did you see the next one? After that you saw that if you are a charged surface, then you do have a perpendicular field. That perpendicular field will be outwards if it is positively charged, inwards if it is negative, given by given by sigma divided by epsilon 0, where sigma is the surface charge density. You apply Gauss law like a pillbox. We will use this when we do a parallel plate capacitor. There will be two plates. That time I will write E equal to sigma by epsilon naught. It should not confuse you. And the last point that you said, that the entire conductor, if it has a cavity inside, then it is shielded, and this is known as electrostatic shielding. There is no electric field inside. So the conductor has a cavity. Inside, there cannot be any charges. If there are any extra charges, they go to the surface. This we already learned. And if you bring any external electric field, then the electrons will redistribute themselves in such a manner. This is point number 1. E inside will become equal to E outside, and so inside the cavity there is no more charge. Such an application is seen in aircrafts, then in Faraday's cage, or protecting sensitive equipments, which you protect by putting them in electrostatic cages called Faraday cages. Our next topic of discussion next class will be dielectrics and polarization. Another theory, but less than this. I can't help it, because if I don't make you write this, there will be many short questions which you'll miss up. Stitch in times, save 9.